So, now we start next lecture, which is lecture 14 on which is now. So, now we have learnt about the crystallography, we have seen the Miller indices. Now we will see how atoms pack in a given structure and give rise to various structures in solids. So, in this series the first material system that we consider is of metals and alloys, and we will see that how atoms pack in metals to give rise to various structures and what can we learn from that. So, the issues that we will address are: 1, how do atoms assemble in solid structures, how does the density of a material depend upon its structure, and when do material properties vary with the, for example, sample orientation. I do not know whether we can be able to do this particular part or not, but we will try and do the first two. Okay. Maybe we will take up some of these in the next lecture. So, the first thing that we consider is the energetics and packing of atoms with respect to energy of the ensembles. So, if you have random packing of atoms, where atoms do not particularly follow a configuration, they are random with respect to each other. So, the neighborhood of each of the atoms is different, some areas are dense, some areas are loose. So, as a result you have you can draw the energy versus distance configuration. These systems, as you can see, these are typically low energy, low density system, okay. Low density system and they have lower bond energy as compared to. So, you are not here, which is the equilibrium separation between the atoms, you are somewhere here, which is the, you can't be here because you are in very strongly lower distance is not possible, because there will be strong repulsion between the atoms. You will immediately get into this region is very steep, okay. So, typically lower separation is not possible, but higher separation is possible. So, you are in somewhere in this region. So, the overall energy of the system, potential energy or the bond energy is lower. So, as a result you are not at the free energy minima, but you are at slightly higher energy. So, whose repercussion is lower bond energy in these systems. On the other hand, you have systems in which atoms regularly pack themselves. So, you have configurations like this, in which atoms are arranged in such a fashion that they touch each other. It's a, I mean, physics wise speaking, they can never touch each other, but they are in close proximity to each other, determined by the energy landscape. And here the energy corresponding to this configuration is minimum, okay. So, as a result they tend to have higher bond energy and they tend to have higher density. So, the density of systems in which atoms regularly pack themselves, which have a periodicity and same configuration of each atom around each other, each atom within the lattice. So, this atom, whether you look at this atom or this atom or this atom, all of them have same neighborhood. So, in such systems they have higher bond energy, they have better stability and they have high density. So, regular packing of atoms leads to high density. So, that is why metals typically tend to have higher density, because atoms are regularly packed in them. On the other hand, if you look at glasses, for example, glasses or amorphous solids in which atoms are not regularly packed in this kind of, they are present in this kind of fashion, there the density tends to be lower. So, we can summarize that structures with regular packing of atoms tend to have higher density and lower potential energy or higher bond energy, okay. So, this is the outline of this particular topic. So, we will see about the packing of atoms in crystals, the close packed planes and directions, packing fraction, voids in solids, perhaps not possible in this lecture, but maybe in this next lecture, and implication of these voids. What do we mean by these voids? What is the importance of these voids in solids, in metallic solids? So, there are two. So, based on the above classification which I gave you in the previous slide, there are two kinds of solids. One is crystalline, second is non-crystalline. Crystalline solids have long range periodicity. As we will see later on, they give very sharp diffraction pattern. So, one way to examine crystalline materials is to use the diffraction, X-ray diffraction, electron diffraction, and they give very sharp diffraction patterns because of periodicity. You know from your 12th standard physics that atoms can be the regular array of atoms can be considered as if it is a regular slit pattern, and you know Thomas Young's experiment when the light or a wave meets a regular array of slits, it undergoes diffraction. So, and diffraction can be noted on a screen or on a detector. So, crystalline solids with regular arrangement of atoms give very sharp diffraction patterns. They have they have a typical melting point. Melting point is well defined. Sharp melting points means well defined melting point. So, for example, aluminum has a melting point of 667 degrees centigrade. It is well defined melting point. Copper has a melting point of 1083 degrees centigrade. It is well defined melting point, and they have crystalline solid typically has higher density. So, all of them, they have variations within them, but since atoms are closely packed, they are touching each other, and the solids are fairly well packed, they have high density. On the other hand, non-crystalline solids, they do not have long range periodicity. So, examples are amorphous materials or glasses or polymers, even many polymers, they do not have long range periodicity, which means the periodicity of atoms do not go beyond, let us say, few tens of nanometers. It is just few nanometers, and after that it is different periodicity. So, they do not have long range periodicity of particular kind. As a result, if you examine them using X-ray diffraction, they do not give very sharp diffraction patterns. So, this is one distinction between crystalline and non-crystalline materials. When you take the X-ray diffraction pattern, in this case you will see very sharp pattern, in this case you will see very in the crystalline case you will see very sharp pattern, and the non-crystalline material you will get very diffuse pattern. Non-crystalline materials also do not have very sharp melting point. Okay, we will see that later on. So, this is another distinction between them. So, when you do thermal analysis to find out the melting point, you will see that there is no very sharp peak in that thermal analysis, and as a result they have they have lower density as compared to crystalline materials. So, polymers typically are lighter, not only because they use they have elements which are lighter, but they also have non-periodic structures which result in even lower density. So, based on you can do another classification based on bonding. The crystals in which molecules are held together by primary covalent bonds, whereas intermolecular bonding could be of weak van der Waals type or hydrogen type. These are molecular crystals such as polymers. Non-molecular crystals are held together. In these crystals, atoms are held together by metallic or covalent or ionic type of bond predominantly. Okay. So, that is why these are the three classes that you can have: metallic, covalent and ionic. Actual bonding may not be completely metallic or completely covalent or completely ionic, it may be a mix of them, but it is normally dominated by one type of bonding, and there are no secondary bonds present there. So, metallic crystals can be defined, you know that they have positive ions, and positive ions core is surrounded by a free electron cloud. Metallic bonds tend to be non-directional in nature. In case of covalency, because electrons are located in certain orbitals and orbitals have a particular shape of them, there is a very strong directionality with the covalent bonds, but metallic bonds do not have a directionality. They tend to be densely packed metallic crystals, and they have several reasons for dense packing. One, typically only one element is present, as a result all the atoms have same radius. So, that allows for, so if you have multiple radiuses present, then there may be confusion which one to choose as a neighbor. So, as a result there may be lack of order, but since you have only one type of element present by and large, they undergo dense packing. As a result, the nearest neighbor distances tend to be smaller, and smaller nearest neighbor distances lower the bond energy, and they have simple crystal structures, and each atoms tend to surround itself with as many neighbors as possible. So, these two are correlated, and then in some cases some metals are partially covalent, and that is why some of them have BCC structure, for example, at low temperatures, and we will see that what is the implication in terms of BCC, FCC structures in the coming slides. We will see that BCC structure is has lower packing density as compared to, for example, FCC structure. So, although we are saying that they tend to be densely packed, at some of the materials are not so densely packed as compared to others, and there are reasons in terms of bonding. So, metallic crystals, typically you can divide them in three structures by and large. FCC structured metals are aluminum, iron between 910 to 1410 degrees centigrade, copper, silver, gold, nickel, palladium, platinum, all of these are FCC structured materials. Face centered cubic, FCC means face centered cubic. Body centered cubic materials are lithium, potassium, sodium, titanium, zirconium, hafnium, niobium, tantalum, chromium, molybdenum, tungsten. Iron at room temperature below 910 Kelvin up to room temperature is even below, it's 910 Kelvin, below room temperature it's BCC. And then there are some metals which are HCP, hexagonal close packed. We have talked about hexagonal system, hexagonal lattice, but we have not talked about hexagonal close packed. We will see what hexagonal close packed system is. Metals like beryllium, magnesium, titanium, zirconium, hafnium, zinc, cadmium, they all are hexagonal close packed structured materials. So, let us first look at the structure of metals by packing of spheres, okay, in space. So, assuming all the spheres are hard, they are incompressible, they are of same size. So, in 1D you can have this kind of configuration, you can have a close packed row of atoms. So, this all the atoms are packed in such a fashion, so they are next to each other along a row. Okay. In the 2D case, the close packed array may be something like that. So, this is the first row, this is the second row. So, this is first, second, third and fourth row. Okay. So, you have the second row goes into the position which is the minimum energy position, where it finds highest number of neighbors with respect to each other. If it goes in this position, it could have gone in this position. So, you have the first row and then you have the second row like this. The difference is, in this case the number of neighbors is lower, but in this case the number of neighbors is higher. On this side you have only one neighbor, on this side you have one neighbor, on this side you will have one neighbor, and on the other side you will have one neighbor. In this case you have one neighbor on, two neighbors on top, two neighbors within the row and two neighbors at the bottom. So, you have 6 neighbors. So, this is called as a close packed plane, the highest possible, highest density plane. So, this is how, if the atoms are spherical in nature, this is the highest atomic density that you can find within a 2D plane. This will be the sort of representation of a plane. It is a hexagonal shaped plane. Okay. You can also say it is a triangle, equilateral triangle, if you can draw equilateral triangle here, but we generally do not use triangle as a representation in lattice. And you have close packed directions. The directions, those depicted in blue are the directions with highest atomic density. Okay. So, this direction, that direction, this direction, they are all. So, how many directions are there within a plane which are close packed? You have 3 directions, and if you take the negative indices around, this is 6 directions. 6 directions within a plane which are close packed, but you have 3 rows of atoms, which 3 distinct rows of atoms which are close packed and which are at equal angles to each other. So, if you look at the close packing of equal sized hard spheres packing in 3D. And this is the first layer which I depict by A. Okay. Then I have a second layer which can go here or here, on top of B or on top of C. So, let us say I manage to put them on top of B. Okay. Third layer can go either on top of A or on top of C. So, if it is AB, 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 then what it makes is a hexagonal close packed structure, and if it is ABC, 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 it will make a cubic close packed structure, which turns out to be face centered cubic lattice. Okay. So, this is how you will have packing: first row, second row, third row, then you put another layer on top, you put another layer on top. This is AB, or first layer, second layer, third layer. This is ABC, ABC kind of packing. So, this one is, as we will see, it will be hexagonal close packed. You have not seen it yet, I am just telling you what it is, and this will be cubic. We will see how. Okay. Right now you do not have any information on how it is, just a word of mouth. So, this is how the packing will look like in 3D: the first layer, the second layer, the third layer, and then the next layer which will again be A layer, then the next layer which will again be B layer and C layer, and so on and so forth. In this case, A layer, B layer, and then A layer. You can do this experiment by buying pebbles or small metallic spheres which are put in cycles. Just make a grid of those atoms, those metal balls, and try arranging them with respect to each other, and you can see that two different structures can be made. So, this is A, B and C, and geometrically it looks something like this. You have, if you connect these, this one lies in the bottom layer. So, this is A, this was B and this was C. All of these atoms are equivalent. I have chosen this to be A, this to be B and this to be C, but I could have very well chosen this as A, this as B, and then A which will come on top of C will become C. Okay. So, in that sense all the atoms are equivalent and their centers form a lattice. So, basically what you have is the motif is a single atom at 0 0 0. Okay. What is the Bravais lattice? Bravais lattice, if you have ABC, ABC stacking, it makes a cubic close packed crystal. If you have motif at single atom, then you need to describe what is the lattice type. Okay. Without that, because so we need to find out what is the lattice type. Okay. Because without that it is incomplete. So, the structure which will look like is in the ABC, ABC packing, it is called as cubic close packed crystal or a FCC lattice with single atom motif at 0 0 0. So, this is the answer here. Motif is at 0 0 0 single atom, but what is the Bravais lattice? Bravais lattice is FCC. At 0 0 plus FCC lattice will automatically mean you have 4 lattice points, one at 0 0 0, another one at half of 0, another one at half 0 half, and another one at 0 half half. Okay. It is, you can form within this unit cell, you can form a structure which looks like this. This is, so you can see that this is the A layer, this is the B layer, this is the A layer, this is B layer, this is C layer, this is A layer, and within this you can form a cube, and the cube interestingly, so this looks like a hexagonal pattern, right? But I am saying that you are forming a cubic crystal, and this is because the atoms are arranged in such a fashion. If you now consider the cube, so this is the cube, right? Within this cube, if I connect the corners of cube with the, let us say, if I connect, what is the arrangement of atoms along this particular plane? This is a 111 type of plane, right? If you remember, 111 type of plane had an arrangement like this, and if I make it bigger in 2D, it will be a hexagonal type of arrangement. So basically all these atoms which are shown here, ABC pattern, they are nothing but 111 planes stacked on top of each other. Okay. So here this is one of the atoms of that 111 plane. These are the few other atoms of that B 111 type of plane, which is the B layer. This is again the C layer of 111 type of plane, and then again you have 111 type of plane of A layer. So within this you can construct a lattice which is called as a cubic close packed lattice, and these atoms are arranged in this plane on 111 plane. So 111 plane in a FCC lattice. So FCC crystal, 111 plane will be the close packed plane. And you can see what are these directions now. Which are the close packed directions? These are the close packed directions, right? What is the indices of these directions? These directions are, if a direction lies within a plane, then the dot product should be equal to 0. So if this plane is 111, then the direction will be 1 bar 1 0, 1 0 bar 1, or 0 bar 1 1. Okay. You can write this as bar 1 1 0, you can write this as bar 0 1, and you can write this as 0 1 1 bar. So these directions which you see on the face, they are the close packed directions, and the plane that you form within the unit cell is the close packed plane, the 111 plane. So this is the FCC unit cell. So this is the close packed plane, these are the close packed planes, this is the direction. This is not the close packed direction, this is just the body diagonal. Body diagonal is perpendicular to these planes. Body diagonal is nothing but 111 type, and for a cube we know that this is perpendicular to 111 plane. Okay. So all the close packed planes are of 111 type. In this case I have drawn the atoms in different color, but they are of different, they are of same color. Okay. Different color is drawn only for illustration, so that you can see two different planes. So this is A layer, this is B layer, this is C layer, then again A layer. All right. So this is what you form as a FCC structure. So this is the stacking sequence. You can say a set of oranges or a set of laddus, sort of. Now let us look at the hexagonal arrangement. Okay. So hexagonal arrangement is you have these 6 atoms in the A layer, then again B layer. I have chosen only 3 atoms, but the B layer can be continuous beyond this 3 atoms, and then again A layer. So this kind of stacking will give me the bottom layer, which is the purple color, the intermediate green layer, the top layer which I have now converted as yellow, but it is the same layer. Okay. So this is my A layer, these are B layers, and this is again A layer, basically on top of each other. Crystallographically you will see it like this. You have A plane, you have B plane, and you have A plane again. So this is basically the hexagonal close packed crystal unit cell. Okay. And the one unit cell that you see is the smaller one, which is the red one, which is called as rhombic prism. Okay. So, it has atoms at, so in this case there will be one atom at 0 0 0, another atom at 1 by 3, 2 by 3, half, and this is a primitive lattice. Okay. Primitive lattice with motif being a combination of these two atoms, motif being combination of atom here and combination of atom here. Okay. So, this is basically the hexagonal unit cell, the smaller lattice, A, B, C axis, the same orientation 120 degree between A and B, and the motif is combination of these two, and if you rotate it, it has a three-fold symmetry. Okay. And the motif, two atom motif, one lies at 0 0 0, another lies at 2 by 3, 1 by 3 half, or you can write it as 1 by 3, 2 by 3 half, depending upon the way you look at it. And because of presence of intermediate layer, that is B layer, in one single layer, if you have just one single layer, the top layer, let us say, you have a 6-fold, right, you can rotate it by 60 degree and still achieve the same configuration, but because of presence of this B layer, now you have lost that 6-fold. So, what you now have is just a 3-fold axis. So, only a 3-fold remains in this lattice, and although I have shown the 3 unit cells here, the unit cell actually is the smaller one, which is the smaller unit cell, which is the rhombic prism, the blue one.
This particular unit cell still is a primitive unit cell.
This is the primitive unit cell because both of them are needed to define the unit cell. So, if you go, these are not two different lattice points. They are not the same lattice points. They are the different lattice points.
They are just associated with.
Yeah. So, you can choose the, so you can put the corner of the lattice between two of them. It is like a dumbbell shaped kind of thing. Okay. So, this is that another representation of hexagonal unit, hexagon closed packed lattice. So, let us see the geometrical properties in this case. You have AB kind of stacking. I have just made them a little smaller. So, here the reason why it is a primitive unit cell, because A and B do not have identical orientation of neighbors. You see, the definition was that each lattice point must be, if it is same, then it must have identical neighborhood. Here they do not have identical neighborhood because of this presence of vacant, let us say, C position, or there is no C position as such. As a result, you need to combine both of them to have identical neighborhood, so that so if you remember the discussion that we have during primitive non-primitive lattices, you need to combine both of them to call it as a proper lattice. So that is why, so A and B do not have identical neighbors, as either A or B as lattice points, but not both. So that is why you need a unit cell contains only one lattice point, but two atoms. Okay, you do not consider both of them as different lattice points. So this is the hexagonal closed pack structure. Okay, so we'll close this lecture here. In the next class, we will look at some other variations of metallic solids like BCC, simple cubic, and we will look at other properties like packing fractions, interstices, voids. Okay, any questions?